Welcome back to CS395. This is Nihal speaking, and this week we are going to be talking about the return to libc attack, which will allow us to bypass debt. So libc is a standard C library that's used in almost every single C program that you write. It's located at this location right here, and this shared object file that's right here, this is loaded in almost every program that you'll write. So whenever you run a program, this file will also be loaded inside of memory. And this file contains things like functions or other things that you might use inside of your program. One of these functions is the system function. So our goal right here in our return to libc attack is we're going to be jumping into the system function, which is located in this file. And we're going to try to execute /bin/sh. The way that we're going to do this is we're going to somehow get /bin/sh into RDI. That is, we'll get a pointer to the string /bin/sh into RDI. And then we're going to overwrite the return address with the address of system. So what's going to happen is it's going to jump to the system function as if we called it. And because system is marked as executable, this should allow us to bypass dep. So there are 4 steps that we need to do in order to do a return to libc attack. The first thing we have to do is we have to leak an address for some data that's inside of the libc library. So what that means is we have to exploit maybe like a format string vulnerability to get a memory leak. And the address that we're leaking must be a pointer to some data that is located inside of the libc library. Once we do that, we are able to calculate the base address of the libc library. Because the offsets should remain consistent if the address is inside of the libc library, we can just add or subtract some offset, probably subtract, and that will give us the base address of the libc library. And then once we have the base address of the libc library, we can use that address to calculate any other offsets that we need. So that includes the offsets to the system function. And then once we do that, we can overwrite the return address with the calculated offset that we found. So the program that we're going to be exploiting today is called libc. So if I just go right here and execute it, you can see that we have a format string vulnerability. So if you just type in, typical format string vulnerability, you'll be able to print stuff off from the stack. And if for the second buffer, it's a stack overflow. So if you just type in, a bunch of A's, this should cause it to segfault. So this is a pretty standard program that we can use to exploit the return to libc technique. So the first thing we have to do when we're given a new program is we have to check what security mitigations are turned on. So we'll go ahead and to do this, we'll just open it in GDB, then run checksec. So what this command will do is it will just print out what security mitigations are enabled on this binary. So right here, you can see that NX is enabled, so we have to deal with dep, and pi is also enabled. So that's something else we have to watch out for. We can also use rabin2-i to print out information about the file. So you can see that it is an x86 architecture. It is a 64-bit file. And we have right here, you can see NX, and you can see pick is enabled as well. And stack canaries are not enabled, so we don't have to worry about that. If they were enabled, we would also have to leak out a stack canary from the stack and use that stack canary when we're overwriting the return address, but it looks like we don't have to deal with that right now. So what we're going to do is we're going to start off by showing you how the buffer overflow works. So if I just do Python and then print out 120 bytes of A's into the second buffer, note that I used a new line character here because we're just going to ignore this first buffer from now, and it's just going to simulate like hitting enter. And for the stack overflow, we're going to put in 120 bytes of A's followed by 8 bytes of B's. Hit enter. And when we open this up into GDB and then run the test file that I just created up here, you're going to see that If I scroll down right here, if I do info frame, it's going to get a segmentation fault. And you can see that the saved RIP value is a bunch of Bs. So after 120 bytes into the second buffer, we are able to overwrite the return address to be whatever we would like. All we have to do is change the Bs to be something else. So going back to the slides, one thing we have to also consider is about the consistency of the offsets that we're using. So during the ASLR lecture, I said something like we could calculate all other addresses from a leaked address because the offsets should remain consistent. However, this is not true if we're talking about an offset for two different libraries or two different files or two different things that are in memory. What's going to happen is if we leak a address that's pointing to data that's in one library or one other process, and we're trying to use that to calculate the offset for a different library, the offsets could actually change because of pi. So what we have to do is we have to make sure that the offset that we're leaking is actually pointing to data that is inside of the library that we're trying to calculate the offsets to. So in this case, we have to make sure that the pointer that we leak is inside of the libc shared object file. So to do this, we are going to go back into GDB right here, and I'm just going to set a breakpoint at main, run it, and then I'm going to use a command called vmmap. So this stands for virtual memory map. And what this will do is it will display where addresses, what the virtual memory address mapping looks like. So right here, you can see that these addresses right here from this address to this address belong to this file right here. So this is the file that we're executing. You could also see that the libc library has been loaded from this address to this address right here. Down here, you could see the stack as well. So the stack also has certain addresses that are given to it, and it can, increase or decrease depending on whether you call another function or do whatever. So what we have to do now is we have to be able to exploit the format string vulnerability, and we have to make sure that whatever pointer that we're going to use to calculate our offsets is in between this start from this end address. Now, right now I have ASLR turned off, but if you have ASLR turned on, then these addresses will actually change. So that's something to keep in mind, is that whenever you're dealing with these two addresses with ASLR turned on, you have to make sure that you check what these two addresses are every single time you run it. But since ASLR is disabled right now, this shouldn't be a problem. So what we're going to do is we're just going to hit continue. And I'm just going to exploit the format string vulnerability again, just so that you guys can see what's on the stack. Now you can see that we've printed out some addresses on the stack right here by exploiting the format string vulnerability. And if you look at the fifth address right here, this is the 1, 2, 3, 4, 5, yeah, fifth address right here. This address is inside, it's pointing to data that is inside of the libc library. So if you look at it, it's 7FFFF7FADBE0. This is in between this address and this address right here. So because the fifth pointer is pointing to data that is inside of the libc library, this is the address that we're going to be using. So we're going to be using the fifth pointer on the stack. If we were to use something like the fourth pointer, this attack would not work most likely, because this pointer right here is pointing to some data that is inside of the stack. So if you look at this address, it's a bunch of it's 7 and a bunch of Fs, then DF80. So yeah, this is inside of the stack because it is between these two addresses right here. And as a result, the offsets will not necessarily be consistent, and they will not necessarily be what we want them to be. So what we're going to do is we're going to create a file. We're going to call it exploit.py. it's going to be a Python file. So we'll put the shebang at the beginning. And we are going to be using Pwn tools. First thing we're going to do is we're going to start the process. So that's just going to be p equals process. And then the name of the file is ret to libc. And then we're going to set stdin equal to pty so that we can interact with our shell. And then we're just going to ignore the very first line because it's not really relevant. It just prints out, I think, format string vulnerability. And then we are going to leak the 5th address from the stack. So to do this, all you have to do is you do p.sendLine, and then typical format string vulnerability right here, %5 $p. This will give us the 5th address on the stack. And we're just going to convert this into an integer using this command right here. And let's just print it out. All right, so we've obtained some leaked address from the stack. We've converted it into an integer, and we're just going to print it out. And I had ASLR disabled within GDB, but outside of GDB, I believe ASLR is enabled. So if I just quickly run this, you're going to see that it is going to have different addresses every single time. But that's not going to matter for this exploit because we're going to make sure that it works even when ASLR is enabled. So the very next thing that we have to do is once we have this leaked address, we have to figure out the offset from this address. And we have to figure out how far this address is from the base of the libc binary or the libc library. So to do this, we're going to go back into GDB, and we're just going to look at this instance of the execution right here. So in this instance, we notice that the 5th pointer on the stack was this thing right here. And if we subtract the base of the libc binary from this 5th pointer, that should give us the offset that we require. So let's just copy that, and let's just go into Python real quick. We will subtract these two values. Is this one right here, and let's convert that in hex because I like hex output. So as you can see right here, the offset is 1BEBE0. So this is the offset that we care about. And this is going to be, if we take this address, the leaked address, and if we add, or if we subtract this value from the leaked address, we will get this value right here, which is the base of libc. So this is the value that we care about the most. So let me just copy that, go back into our exploit. And we are now going to calculate the address of, or calculate the base of libc. So we're just going to say that libc's address equals the leaked address minus that, that offset that we just found just now. And let's just print that out as well. So libc plus this thing in hex. And if we just go in and execute this file, we can see that it is able to calculate the address of libc. And again, this is going to change every single time because of ASLR, but it's going to, this offset value should remain consistent because the leaked address was a pointer to some data that was inside of the libc binary. So we shouldn't have to worry about ASLR in this case. All right, so the very next thing that we want is we want the address of the system function because we are going to be jumping to that function. And so what we can do is we can't directly just get the address because ASLR is enabled, but what we can do is we can use a tool called readelf. So what readelf does is if I just hit enter, it'll print out data about elf files. So we're going to print out some data about the from the libc shared object file. And we are specifically going to be printing out the symbol table. So this symbol table will give us information about the offsets. And just to show it to you, if we do read elf-s and then just this right here, the file that we're trying to read is the file that I explained earlier, which is the libc shared object file that contains the library itself. So if you hit enter, you get this huge amount of data, but we don't really care about most of this. So we're just going to pipe that into grep, and we're just going to grep for system. So this is only going to print out information about the system function. So if you look right here, this contains information that we care about. This is the system function that we want to jump to, because when we jump to this function, it is going to be able to give us a shell. If we look right here, we can actually see the offset. So this is the offset from the base of libc. This is not the offset from the leaked address. This is the offset from the base of libc. So what we can do is we can take this value right here, this hexadecimal value, and we can add it to the libc base address that we found earlier. So I just go back into Vim, calculate the address of system. So we're going to say system address equals, and then we're going to use a p64, and we'll do the base of libc plus that offset that we found just now. So again, this command right here will print out offsets for various functions that are inside of this library right here. We found out that the offset from the base of libc for the system function is this value right here. And we're just going to add that offset to our base of libc right here. And we use p64 to convert it into little endian format for us. So we can now just print that out as well. And when we execute this, we will see that it is able to calculate the address of the system function that we care about. So the very next thing that we have to do is we have to somehow get the /bin/sh string into our binary or into our exploit right here. And we're not going to do what we did earlier in like week 2, where we were able to push it onto the stack. We're not going to do that. Instead, we need it to be inside of RDI, because the x86-64 calling convention states that if you're calling some function, the very first parameter should be in RDI. So we have to figure out how we can get a pointer to the string /bin/sh and put that pointer in RDI. So before we talk about how we get that pointer in RDI, we need to talk about where that string is located. Now, if I go back to this right here, and I'm just going to Control-C out of this and do VM map again, we can see that we have all of the libc library mapped in memory right here, because it gets loaded for almost every C program that we write in Linux. So one thing that's cool about the libc library is that it actually uses the /bin/sh file in certain areas of its code. I'm not sure exactly where it's being used, but it is being used somewhere. And for that reason, this inside of this memory right here, there's actually a string, there's actually a pointer to the /bin/sh string, and we can just search for that. So the way we can search for that pointer is we use the find command inside of GDB. We'll put in the start address, which again might change because of ASLR. We put the ending address, which is right here. And then we put in the string that we're trying to search for. So we're just going to search for the /bin/sh string. And as you can see right here, it was able to find the string right here. So if we use examine string and then just copy this, paste it in there, we can see that we do have access to the string. So now what we need, because of ASLR, we can't just use this address directly. We need to get an offset and then add that offset to the base address of libc. So to get that offset, we can just take this value and subtract the base of libc from that value. So take that, take the base of libc, convert to hex, and this is the offset. So what's going to happen is if we're given the base of libc and if we add this value to the base of libc, we will get a pointer to the string that we care about. So let's go back into our code again. And we're just going to add that to the code. Just like that. And so now we have the address of the string right here. And if we run this again, it works. It will print out the address of the location of that string. So the next thing that we have to do is we have to figure out a way so that we can get a pointer to the string, which is printed out right here. We need this pointer right here to be inside of RDI, because like I said earlier, the x86-64 convention states that the very first parameter must be inside of RDI. So we can use a ROP gadget to get this done. So I'm going to use Ropper to do this. I'm going to search inside of the, instead of looking inside of the ret to libc file, I'm going to look inside of the, this file right here, the file that contains all of the libc code, so that we can just calculate an offset from that file. So we are specifically looking for a pop RDI instruction. And the reason we're looking for that is what we can do is we can just put this address onto the stack, and then it's just going to pop that address off of the stack and then put that inside of RDI. So as you can see right here, this is the offset that we care about right here. There's a lot of choices right here, but we're specifically going to just choose this one because it does exactly what we want it to do. We don't want, you know, any of this other crap to happen as well. We just want it to pop RDI off of the stack and then just immediately return. So we're gonna copy that address right there. Go back into our exploit. Calculate the address of pop RDI. And so we're just going to do what we did earlier and just add that address to the base of libc. And of course, print it out. Just like that. And then now we can run our exploit, and we get this address right here. So this is the address of the pop RDI ROP gadget that we're going to be using inside of our ROP chain later. The very last thing that we need is, this is sort of optional, but we're going to add the exit function to the end of our ROP chain. So what we're going to do is we're going to use the readelf command that we used earlier, except instead of grepping for system, we're going to grep for exit. There are a few options here, but we're concerned with just the regular exit function right here, which has this offset right here. So we're just going to add this to our exploit. And if we execute our exploit, you can see that the address of the exit function is also being printed out here. So the very last thing we have to do is we have to actually trigger the buffer overflow and have our ROP chain execute. And so this is how our ROP chain is going to work. First, we need 120 bytes of A's because, as I mentioned at the very beginning of this video, we need 120 bytes in order to overwrite the return address inside of the second buffer. So once we get those 120 bytes, we are going to create our ROP chain right here. And the very first thing that we're going to do in our ROP chain is we are just going to call the top RDI address ROP gadget right here. So what's going to happen is we're going to have the very next thing on the stack be popped off, and it's going to be saved inside of RDI. So the next thing that we want on our stack, because we need these /bin/sh string inside of RDI, we want this to be the very next thing on our stack. So that way, when this pop RDI occurs, it's going to pop off this thing right here. And then it's going to allow us to call the system function right after that. So we can just add that right there. And then right after that, at the very end, we are just going to call the exit function so that we just have a clean exit. And then we're just going to send this payload over, and we're going to make it interactive. So let's just run this exploit. And as you can see right here, it works just fine. So just to recap what we just did right here, we created the process using a typical Pwn tools process function. And then we were able to leak an address from the stack. The fifth address on the stack was pointing to some data that was inside of the libc library. So that was why we specifically chose the fifth address on the stack to calculate our offsets from. Once we did that, we were able to, we knew that the fifth address on the stack was this value away from the base of libc. So we just had to subtract that value from this leaked address to get the base of libc. Once we did that, we were able to calculate the addresses of system of the /bin/sh string and the pop RDI gadget and the exit function just using this one base address that we calculated earlier. To trigger the buffer overflow, we first started having 120 A's so that it would overflow the buffer all the way up until we hit the return address. We overwrote the return address with the address of a pop RDI instruction. And so what would happen is once this instruction was hit, it would pop the /bin/sh pointer off of the stack, and it would put that inside of RDI. Right after that, because this is a ROP gadget, it ends with a return. So the return is going to pop the system address right off of the stack, and it's going to jump to that address, and it's going to execute our shell just like that. And then we just have this exit function at the very end just so that we have a clean exit from our ROP chain. And we just send that all at once, and we get a shell. So just to show you how this looks like inside of GDB, if we do, what is it? gdb.attach, we can actually attach a GDB instance, and then the second string right here explains what commands we want to run inside of this GDB instance when it's executed. So what we'll do is we'll set a breakpoint at main plus 110. And by the way, if I just disassemble main right here, main plus 110 is just the return. So it's just going to set a breakpoint at the very end of the main function just so that you guys can see what's going on. And then we're going to use a new line character to indicate a new command. And then we're just going to use the continue command. So just execute that. It's going to open up GDB for us, and it set a breakpoint at main plus 110 like we asked it to. And as you can see, the return address has been overridden with the address of a pop RDI instruction. So if we use NI to go to the next instruction, we go to that pop RDI instruction, If you look at the stack currently has a pointer to the /bin/sh string. So when we pop that off, that pointer is going to go inside of RDI. So if I just scroll up, where's RDI right here? So if you look at what RDI is equal to, you can see that RDI is in fact pointing to our string. Next thing that's going to happen is we are going to hit the return. If you look on the stack, the next thing in the ROP chain is our system function right here. So we're going to jump to the system function. So once we jump to the system function, we are inside of the system function, and then the program will do whatever the system function does in order to open up a shell for us. So if I just disassemble starting from right here, we can see that this is what the system function looks like, and it's just going to execute all that code for us so that when we hit continue, and let's just X out of this, we are able to get a shell for our exploit right here. So that is how our ROP chain works. That is how the return to libc attack works. It's a very useful technique that you can use to jump to any function that is inside of the libc library. So your homework for today is you should start working on your final project if you haven't already started working on that project. I also want you guys to continue studying the return to libc technique on your own. Anyways, that's all that I have for you all today. Thanks for watching.